Reading week 13. This week's main physics idea was electromagnetic radiation, and we looked at Maxwell-Ampere's law, which shows that the circular integral of B field over dl is going to be equal to mu naught times I plus mu naught times epsilon sub 0 times the d over dt of integral of E field times the normal vector over the area that is going through. And so we looked at the idea of electromagnetic radiation, and we know that EM radiation is applied to source with a accelerating charge, and we know the direction of the unit vector for the velocity is going to be equal to the unit vector of electric field and magnetic field. And we know the speed of light is equal to the magnitude of the velocity, which is 3 times 10 to the 8th meters per second. And we also looked at a radiative E field of a point charge, and we know the equation equals to E of radiation equal to 1 over 4 pi epsilon 0 times negative Q times acceleration, which is the perpendicular component, over the c squared, which is the speed of light, times the magnitude of r. And we know we can find c equal to be the magnitude of E radiation over magnitude of B, which is the magnetic field of the radiation. What I already knew from the previous weeks was the idea of Gauss's law and Faraday's law for calculating E field, but I was not aware of anything that's called Maxwell-Ampere's law and the radiative E field. And I always thought that the electric field was just going to be one type where we learned with the Gauss's law and Faraday's law, and we calculated using E equals 1 over 4 pi epsilon 0 times Q over r squared times the unit vector r, which is the E field equation for a point charge. But now a new thing that we learned is that you can also find a radiative E field when that point charge that you found is actually accelerating in a such direction. And on the right, you can see the electromagnetic spectrum that we used to see in high school science classes. And on the bottom, we know the relationship between the electric field and magnetic field, and that they are perpendicular to each other. Something interesting that I learned this week was that an accelerating charge can radiate electromagnetic fields, and I just did not know that a charge can not only create an electrostatic field but also electromagnetic field that is radiating. And how it relates to my major in terms of electrical engineering is that electromagnetic EM, which is the study of underlying laws that govern the manipulation of electricity and magnetism. And it also relates to how we use this law to our advantage. And electromagnetics is actually a source of fundamental physics principle behind many branches of electrical engineering, and it therefore indirectly impacts many other branches, and probably one of the branches that I will focus on to in future career. A confusing topic for me this week was the idea of electromagnetic radiation, and so I've never heard of EM radiation before, and this concept was kind of new to me. So I searched it up on Google and found that this description actually described in terms of easier way to understand what a EM radiation is, and it is a form of energy that is around us and takes many forms. For example, it could be radio waves, microwaves, X-rays, or gamma rays. And they said the sunlight is actually an example of EM energy, but visible light is only a small portion of the EM spectrum, as you saw on the first slide, and therefore it contains a broad range of electromagnetic wavelengths. And an interesting theory that I read online was that in 1873, the Scottish physicist James Clerk Maxwell, as you can see on the top right, he developed a unified theory of electromagnetism. And the four main interactions that he discovered are actually the ones that we covered throughout the entire course of Physics 2212, which is the fact that the force of attraction or repulsion between electric charges is inversely proportional to square of the distance between them. That's related to the E-field equation that we learned. And the magnetic poles come in pairs that attract and repel each other, much as electric charges do, and that kind of relates to the dipole moment. And we looked at electric current in a wire that produces a magnetic field whose direction depends on the direction of the current. And we know that from our right-hand rule. And lastly, a moving electric field produces a magnetic field and vice versa. And so that's related to our idea of electromagnetic theory.